Okay, so our quick look at the calendar. Let's highlight today. Here we are, May the 1st. Happy May. Today we're going to talk about Taylor series, just like Taylor polynomials, but series means maybe we go forever, and so we're going to take those polynomials from last class and have infinitely many terms instead of just 6. So that's the plan for today. Next class, which is Monday, we will manipulate Taylor series and see how to use them to do some stuff. Wednesday coming up is our review day for test number 3, which is a week from today. Okay. The test is on everything from the last test, which was 1 day on sequences, and everything else on series. Yeah. Okay, questions on the calendar? Project is Monday. All right. So, page 51, daily summary, Rich.
This class features Taylor series, what happens to Taylor polynomials.
Good, number 1, Rich.
In the last section, we looked at Taylor polynomials. Each of these polynomials has a definite stopping point. Example given here before. In this section, we look at Taylor series with n infinity.
So there's our formula from last class. We saw the factorials, we saw derivatives of various orders, and we just stopped at particular ending points. And now we're going to try to let the Taylor polynomial go forever. Number 2, Rich.
For example, let's find the Taylor series including general term for f of x. Here, x equals 0. This is actually called a Maclaurin series.
Okay, so brand new definition, Taylor series and Maclaurin series. Taylor series is just what we did last time, but with infinitely many terms in our polynomial. Maclaurin series is a specialized one where the center happens to be 0, which is x equals 0 that we've got here. In fact, why don't we use the same letter we used last time? A is what we were calling the center. Exactly. So using Taylor series on polynomials is kind of silly because you'll eventually just get back to your polynomial. Yeah, but we're going to do it for e to the x. Let's give it a shot. So we're going to do some stuff that's quite similar to what we did last time. We'll see. So we're going to list a few derivatives here. What's the first derivative? E to the x. Second derivative, e to the x. So you list enough until you get the pattern. I'm content that we have the pattern. All right, we'll do the next one will be harder. All right. Next one, we're going to do in another color over here. Let's do f of, what's the magic center number? 0. So we're going to do f of 0, f prime of 0, f double prime of 0. 1 and 1 and 1. Good. Again, I'm happy enough that we have our pattern here. So all of these derivatives will be 1. And so now it's a matter of writing our formula. We've got this big, massive Taylor polynomial formula at the top. So here we go. P sub n of x equals, okay, so it says f of 0, all these a's are going to be zeros, so f of 0 is 1 for us. So we go 1 divided by 0 factorial times x minus what number? X minus 0, all those a's are 0, raised to the 0. So I'm just going to go very slowly here. That term is this term. Yeah, it's just a 1. Next one, plus. Now we're doing f prime of 0. How much is it? That's a 1. Divided by what? 1 factorial times x minus 0 raised to the 1. Different color. That is the next term. Go ahead and write down the next 2 terms after this guy. 2 more terms. Okay, so 1 over 2 factorial x squared, 1 over 3 factorial x cubed. Now, here's the difference between yesterday or last class and this one is that now we're trying to go to a generic n. Instead of stopping at cubed, we want to stop at the nth term. We want the general term, same idea that many of you are doing on the project that's due on Monday. So we're going to do a plus, dot, 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 plus, and then we're going to jump all the way to the nth term, which is a very general thing. Why what? Because this is my way of saying that there's some indeterminate number of things in between, and I'm just jumping to the last one, which is generic. Yeah, plus some stuff, plus this last guy. And then, okay, so what's the numerator for all of these? 1 over, what's the factorial when we're doing the nth term? Is n factorial, x minus 0 raised to the n. Perfect, that's the last term, it's the general term. And so that means that we can then use sigma notation. So how about we copy our general term here? 1 over n factorial x, I'll just write x to the n. And this guy starts with n equals what? Back in the yellow? 0. That is a poor choice of letter. Sorry. Sorry. 1 over. N is going to be my stopping point here. I needed to use a different letter than n in here. So any other letter I, is that our standard one? So I see an I factorial and then an x to the I, starting at I equals 0 and going up to n. N is our ending point, and even though we're treating it like it's some constant number, so it shouldn't be the varying thing in the sigma. Yeah, and then we're going to send it to infinity in a second. Okay, so that right there is our. That's it. We're done. That's our nth degree Taylor polynomial, and so what that means is that e to the x is equal to that guy. I equals 0, 1 over I factorial x to the, we're kind of doing something here. We're good talking about Spanish punctuation. Done? Yep. Okay. Okay, so if I want to get better and better, closer and closer to the function e to the x, where should I send n to infinity? So how about we just put it there? So e to the x is essentially that polynomial if we let the polynomial go forever. I'll write out the first few terms just in a nicer form. 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24. These are just some of the factorials written out. The more terms you use, the closer that polynomial approximates e to the x.
First, second, third, fourth derivatives are all.
Yeah, so we'll do a tougher one as our second example. This is the easy one, right? We start easy. Okay, let's find the interval of convergence. We have a series. We've got its generic term. What test can we use to figure out what the interval of convergence is? Ratio test, just like on the project. Use the ratio test 5 times, I think. So let's do the ratio test. So our generic term is this last guy up there in purple or here in black. So ratio test. Ratio test involves a limit as n goes to infinity. I guess I is going to infinity now. And n is throwing me off. Okay, so what do we have here? So it's the replace all the i's with I plus 1s, yes? So we get 1 over I plus 1 factorial times x to the I plus 1. Yeah, you can make it one fraction. I'm going to write it in details here. 1 over I factorial x to the I. Right, that's the general term on the bottom, and then the next term out in the series on top. What are we missing? Absolute value, gotta have it. Okay, let's do some canceling. We'll just imagine flipping things over because I don't want to write a lot. What happens to the x's here? 1x left over on top, I'll put it there. This I factorial flips over and goes all the way to the top. So what happens when I cancel some factorial stuff here? Is it I on the bottom? I plus 1 on the bottom. That bigger guy, one thing is left over. It's there. As I goes to infinity, the limit goes to 0. Right? I is left over on the bottom. Magic number for the ratio test is less than 1 in this case. Len? No, so this is some more factorial algebra. So it was an I factorial on top and an I plus 1 factorial on the bottom. And the guy on the bottom is 1 bigger than the guy on the top. So there's going to be just the single biggest number, I plus 1, left over on the bottom. And if you want to tie that into some reality thing, just imagine 9 factorial over 10 factorial. You'll be left with just a 10 on the bottom. Okay, so this is a special case. So what does this mean about our series? Converges everywhere, right? Because 0 is always less than 1. So the series, or we'll just say, so the IOC, interval of convergence, is minus infinity to infinity. That would, it's no different. It's just specialized to the center being at 0 as opposed to 1 or pi. That's all, just a name. It's named after a guy. Okay, so the next page. So like several of you have seen, this was an easy example because it was e to the x, right? But now we're going to imagine taking the derivatives of ln of 1 plus x, and we're going to do several of these derivatives, and the derivatives are not going to be nearly as nice as the e to the x one, right? But let's start off exactly the same as we did before. F double prime of x equals, okay, I'm going to start with 2 derivatives here. We might need 3 or 4 or 7. We just got to do as many as we need to until we see the pattern. That's the goal. So there isn't something where I'm going to say you got to do this many. You just got to do enough to get the pattern. There will be a pattern. Okay, so the original function I'm copying, ln of 1 plus x. What's the derivative? 1 over 1 plus x. Don't copy that. It's correct, but don't copy it. How do I find the next derivative? So what rule? So quotient rule, right? Which is kind of messy. Can we write this in a different way? Do we buy that? And taking the derivative of this guy is going to be nice. It's going to be equivalent, but it's just going to be nicer and easier for us to do some pattern finding. Okay, so let's write down the next derivative. So -1 comes down. 1 plus x to the -2. Normally there's a chain rule, but what makes this guy nice? It's just the derivative of x is just 1, right? Okay, I still don't see the pattern. Let's do another one. F triple prime of x equals, right, because that 2 is going to come down, right? No, -2 comes down. So 2, 1 plus x to the -3. How about we press our luck? One last one. It is -6. I'm not going to write -6. I'm just going to write -3 times 2. Because that's a factorial, yeah? If you write it as 6, you might lose the fact, like it's a factorial popping out here. Do you see it? the next derivative, I'm not going to write it, but there's going to be a -4 coming down and joining its friends 3 and 2. And you can then go back and then you can see, oh yeah, there's a 2 factorial, a 1 factorial, 0 factorial, and then the original is just an outlier. It's got an ln. It's okay. Okay. All right. We are going to take a number and plug it in for all of these x's. It's given in the problem. What is it? 0. It is not always near 0, but in this problem and the previous one, it was 0. Do we see that? It's in the problem. So plug 0 in for all of those x's. So when we plug 0 in for the x, the thing in the parentheses is 1 every time, which is kind of nice for us because 1 to any of those powers is always 1. Now, if you just make up a random function and you have to find 5 derivatives, like they're going to be terrible, right? So you're going to be given very well-chosen examples that will make pattern finding reasonable. All right, so now we just got to churn through our formula here. So we're going to do this one not as detailed as the last guy. So P sub n of x equals. Okay, first term is 0 plus 1 times x, right? X minus nothing is just x, and that's raised to the first. Next derivative here is a -1. X to the 2 divided by 2 factorial, which if you feel like that's just coming out of nowhere, it's only because we didn't write it for the other ones, right? This is over a 1 factorial. That's over a 0 factorial, no problem. Next one. Plus 2x cubed over 3 factorial. That is a 2 factorial if you want to put it there. I'll do one more. Minus 3 times 2 over 4 factorial. Yeah, 3 factorial on top, 4 factorial on the bottom. All of a sudden we have more canceling. What are the denominators if you cancel some factorial stuff? Right, this bottom denominator, that 4 factorial, the only thing left will be just a 4. Right, the 3 and the 2 will cancel. What's left in this previous guy? Just 3, because the 2 will cancel. The first term is just plain 0 because of the top. Yes. Right, and that's why I said the first guy is just an outlier. Like the first guy had ln, and it's not going to look anything like the derivatives that we just did. Okay, so plus dot dot dot. Here's the hard part. Hard part is coming up with the general term. We'll start with the x. X to the n. That's just going to be it every time, right? Although normally it'll be x minus some number that you have to write down, x minus a to the n. Okay, the bottom is also it's normally n factorial, but I want to take advantage of the pattern that we just found. It's just plain n because it was like becomes just plain 4 and just plain 3, right? What's that? Yeah, the top is an n minus 1 factorial, and then it becomes this. Right. Okay. All right. So we'll include it. So right, that's really what it is, and then it becomes x to the n over. We need to, right? Because there's an alternating thing happening. So we'll just deal with this guy last. Okay, so we got to make sure my default is an n, and then if I need to fix it, I'll put a +1. Let's just pretend. Thank you. Okay. So just look at the powers and the plus or minus ones. When it's an x squared, it needs to be negative. When it's an x cubed, it needs to be positive. Is that right? If I square it, is it negative? No. So let's add 1 or subtract 1 or 7. Okay, so I'm running out of space here. I don't know where you're going to write this. I'm going to grab some space here. Sum I equals. All right, so we're writing our generic term, right? X to the I over I factorial. Just over I. That's good because I'm having trouble with the i's and the factorials. Just over I, and then -1 to the I plus 1. All right, so that's just our general term. And then you have to make it start at the right spot. So what's our first non-zero term? It's just this 1x. So what power is to the 1? So starting at 1 will get us that first term. Plugging 0 in means dividing by 0, which is a problem. Well, yeah, I mean, we're saved by the fact that there's a 0 on the top there. Okay, so this guy goes from I equals 1 up to n. We've got it. The series has an extra term, which is 0. If that extra term were not 0, like if it were a 5, well, I'd just put it outside because it doesn't follow the pattern. And I can't start this guy at I equals 0 because there's an I in the bottom. Sure. Great. All right, you can put as many as you need to. We just got to capture the infinite part in a pattern. Right. Okay, so here's what I want us to do. So I'm going to end there, but I want you guys to start the activity, but not the activity. I want you to start by finding the interval of convergence of this guy that we just wrote down. Okay, again, I don't know where you're going to put this because there's no space on this page. It's not the way I wrote it, but you got to find the interval of convergence, ratio test. There might be some endpoints to test separately. Again, all of today is good practice for that project. So see how far you can get and raise a flag if I can help.